Hello, Metrics Nation, and welcome to our third lecture of our online spring 2020 econometrics. Again, we're going to be talking about instrument variables. And this time, what we're going to be talking about is the variance of the estimator. So let's go ahead and open up the presentation that I'm going to be using. This will be posted in one form or another to the website if you're interested in looking at it that way. So when we're talking about the instrument variables variance, just as a reminder, here's our setup. We have our instrument Z that we're separating out our X into an exogenous component, X hat, and we're left with the endogenous component, which we will just leave with the error term. In equation form, I added a little bit here. We've seen this before, but I want to emphasize that we often do this in a multivariate setup where we have an x2 as well as just our x1. Again, we're worried about endogeneity here, where the error term and x1 are potentially correlated, but we found a valid instrument that is related to x and unrelated to the error term. And so we're doing two-stage least squares to get around this problem of endogeneity. And in our first stage, we're using an auxiliary regression to break X out into its two components. The first component is going to be the endogenous component and the exogenous component. Now, again, here, I've emphasized that when we have other regressors, X1, X2, X3, X4, that those actually become part of that first stage. They're included in the first stage. In our second stage, we are going to use X hat in place of X. So in only using a portion of X hat, we are getting rid of our endogeneity problem. So let's get to the main point of this lecture, the variance of our estimators. So this equation hopefully is familiar to you at this point. This is the variance of beta hat when we're using ordinary least squares. So we have our sigma squared, which is the variance of the error term. We have the variance of X itself. N is the number of observations, and 1 minus rxj squared is that variance inflation factor. How is X related to all those other factors? For our two-stage least squares variance of beta hat, it's very similar. Now, I've emphasized that our variance of the error term is different by putting a little prime there. It's still a variance of the error term, but it's a different error term. We have no longer variance of X in the denominator, but variance of X hat. We still have N, and our R squared has changed as well. So let's start out by talking about how these differ. So now we're going to look at the variance of the error terms in two-stage least squares versus the variance of the error term in OLS. But first, let's talk about how this error term works and how it's broken down. Just to remind you here, we have our equation, and what we're doing with our two-stage least squares is essentially through our instrument, we are breaking X into two components, X hat and X tilde here. And so we are going to be ignoring, for two-stage least squares, the endogenous portion of X. So the error term in our two-stage least square with the prime here is going to be the original error term if we could have done OLS and gotten an unbiased estimate, plus beta 1 times our x1 tilde. You can see that these are the same things here. And so when we're doing our two-stage least squares with x hat, our error term is that error term prime. And what we're curious about here is the variance of the original error term compared to the variance of the two-stage least squares error term. And we can see through this equation that generally the variance of the error term in the two-stage least squares is higher than the variance of the error term when we did not have to do two-stage least squares. This isn't strictly always true. We know that there is some correlation between x and the error term itself, the original error term, and in some rare cases, it could be that that correlation is both negative and large enough that this might not strictly hold, but as a rule of thumb, this is going to be the case. So when we're looking at the variance of beta hat, and we know that it's depending on the variance of the error term, we know that generally we have a smaller variance with OLS, the error term, and a larger variance with two-stage least squares. The next component we'll look at is the variance of x. This is a very sort of straightforward. We're going to compare x versus x hat in this particular instance. And we can just do this by looking at an equation here. So x is directly related to x hat because that top component of the delta 0 plus the delta 1z, that is x hat. So x hat is a subset here of x in a sense. It's a portion of it. And so the variance of x we could write as the variance of x hat plus x tilde. Well, the way that we're linearly constructing these, x tilde is independent from x hat, so we can break out that variance, and therefore we have the variance of x hat plus the variance of x tilde. Well, we also know that that variance is not going to be 0 unless we have an absolutely perfect instrument. That won't be 0, so it will be greater than 0. That mathematically simply implies that the variance of x is greater than the variance of x hat. Now, when we think about this, thinking more intuitively, when we're using an instrument, what we're doing is looking at one factor that is determining our x variable. So we had talked about the example of good internet access, determining whether or not you're able to attend online office hours. Now, this will be one factor, but it won't be the only determining factor in whether or not you can attend. And so the variance that we are getting, the movement that we're getting from that one factor, isn't going to be as big as the variance of the whole. Some people will show up, some people will not, and that will depend on other things other than just internet access. In general, though, connecting this to the instrument, if the instrument is better, if it's stronger, the better the fit this that we have, the closer the variance of x hat will be to the variance of x. And therefore, the closer the variance of beta hat in the two-stage least squares will be to the variance of beta hat in OLS. So just to emphasize, here we have a larger variance of x, a smaller variance of x hat. And this means for the variance of beta hat versus OLS versus two-stage least squares, that OLS is going to be smaller than the two-stage least squares. Our final thing we're going to just talk about very briefly is the variance inflation factor. It's not as straightforward as the other ones, but just to emphasize what these are, again, this is an auxiliary regression, but it's not the first stage auxiliary regression with the instrument. Here, this is how is x correlated with all the other x's. How is x1 correlated with the other x's? That's that r xj squared, r squared from the auxiliary regression. We'd use correlation. That's only good if we have two. We're doing something very similar here, but instead of x, we're using x hat. That's the only difference. However, I do want to emphasize that all these other x's are part of the definition of x hat. And so the only difference of x hat has there versus the version with the betas, the version where we're looking at the rxj's, is that we have the z in the determination of the definition of x hat right there. So again, the better fit we have with our instrument, the smaller the r squared of xj will be. The more that it's just coming from x, sorry, that the x is just being explained by z and not the other x's, the more so that those other x's won't be related. There isn't sort of a definite, it's going to impact your variance this way or that way. There's not sort of a necessarily known direction here for this one. Putting these together, not a known direction for the variance inflation factor, generally larger when we're talking about the error term, generally smaller for two-stage least squares when we're talking about the variance of x, and therefore the variance of beta hat itself is generally larger with two-stage least squares than with OLS. So just to sum up, we're talking here about the three things that impact the variance of our estimators. Variance of the error terms, generally larger for IV. You can see that in this equation. The variance of x is generally larger than the variance of x hat. We can see that in this equation here. And the variance inflation factor, also related to the first stage, but doesn't necessarily have a consistent sign. All right, that is it for this lecture 3. I hope you all are hanging in there, doing well. Please let me know if you have any questions, post them up on Moodle, and I hope to be interacting with you soon.